In this video, I'll go through how I solved my heat plate / reflow problem. In the last video, when I made the Bitex hex, I had trouble with heat transfer and the size of the board. It made reflowing the board manually really challenging, and repairs or fixes would have been very difficult. I needed a solution that is stable, safe, and controllable, and that works the same way every time. And yeah, you're looking at the result right now. Now follow me, and I'll show you how I built this. For the frame, I started by cutting all the T-slot profiles to length. I used a miter saw with a wood blade, but it had carbide teeth, so it cut the aluminum without any problems. After cutting everything, I measured and marked the positions for the mounting holes. Then I drilled all the holes I needed for the frame, so the rails and brackets could bolt together straight and rigid. Next, I'm designing the armature in CAD. I'm making it as a foldable part from 2mm aluminum sheet, and I'm adding grooves so it bends exactly where I want. Once the CAD is ready, I export it and bring it into Kirimoto. Here I set up the tool, material thickness, cut depth, and generate the toolpaths. After that, I export the G-code, move it to the CNC, and set up the workpiece. On my CNC, I'm using plywood sacrificial plate, so I can safely cut through without damaging the machine bed. To hold the aluminum sheet, I use double-sided tape underneath, and then I also clamp everything down to make sure it cannot move. Now I zero the machine, do a quick test move, and then I start the cut. I run it in multiple passes, and I stay close to the CNC the whole time to make sure everything sounds and looks right. When the job is done, I remove the part, clean up the edges, and make sure all the cuts are clean and the holes are the right size. For the connector piece that mounts the power box to the plate, I'm not using the CNC. I'm making this part on my homemade milling setup. It's fine for light aluminum work and small cuts, but it's not for heavy-duty machining. The spindle head is press fit, so if I push it too hard, the head can come loose, like it does right now. That's why I always run it at a low RPM and I only take light passes. Even if something slips, it won't be dangerous at that speed. Now I'm bending the aluminum to make the armature. For the bending jig, I'm keeping it simple. I'm using scrap wood pieces with a gap between them, and I screw them down so they don't move. Then I line the groove up with the edge, and I bend along that line. Because the grooves are already there, the bends are really clean and easy, and the angles come out consistent. I just go step by step, bend each section, and I keep checking that the armature stays straight and square. Now I'm drilling and tapping mounting holes in the hot plate so I can fasten the aluminum plate securely on top. I drill the holes at the edge of the hot plate because I know the heating element is not under that area. Then I tap the holes to M4 and clean out the chips. I mark the positions, drill the holes, and deburr them so the parts sit flat. Then I line everything up and attach it using aluminum rivets. The rivets make it strong and permanent, and it keeps the frame clean without extra bolts sticking out everywhere. Now I'm moving to the electronics. I start with an ESP32-2432S028, the CYD board, controlling a Cridom D2425 solid-state relay and reading a 100 KNTC temperature sensor beta 3950. First I build everything on a breadboard, just to prove the basics, that the sensor reading is stable, the relay output switches correctly, and the UI works. The first big problem is the display software. I try LVGL, but it doesn't compile cleanly because the project is missing lvconf.h, and I also hit the version mismatches between LVGL v8 and v9. So I switched to a simpler and more stable setup, TFT_ESPI for the display, and XPT2046 for touch. Then I fix the split screen, noise, black screen issue by configuring TFT_ESPI correctly for this board. I use the right IL-I9341 driver variant, and I enable the inversion setting so the colors are correct. After that, I improve the touch behavior by debouncing the touches and by updating only small parts of the screen instead of doing full redraws, so the UI doesn't flicker. For testing, I use a desk lamp and a hot air gun as a simple heat source. I just want to see the temperature react correctly and see the relay switching the way it should. Once everything is working reliably, I move the wiring from the breadboard to a small perf board and I add JST-style connectors so the sensor and relay wiring can be plugged in cleanly. I'm also going to make the code public on GitHub, and I'll upload the schematic for the board as well, so you can build the same thing if you want. On the perf board, I don't make traces by piling up solder. Instead, I lay down a thin stranded wire to act like a trace, and I solder it into every hole along the path. That way it becomes a solid connection. It's cleaner and it's much easier to control than a big messy solder bridge. And here I wasted a lot of time because I make a really stupid wiring mistake. On the ESP board, I'm supposed to take 3.3 volts from CN1, but instead I accidentally take power from a signal pin on the P3 header. The pins had the same color and pin number style, so I mixed them up. The problem is that the signal pin can give a little current, so it looks like it's working. But when the MOSFET turns on and the relay circuit pulls current, the voltage drops and the sensor loses power. The sensor resistance drops and the code reads it like a sudden temperature spike. I thought it was noise or interference, so I rewired everything and even rebuilt the board several times before I finally found the real cause. After I moved it to the correct 3.3 volt pin, everything worked normally again. Then I do the same lamp and hot air test again on the final board, and now the temperature reading and relay output are stable. I designed a 3D printed enclosure for the electronics. I wanted everything in one safe box: the solid state relay, the 5 volt phone charger for the ESP32, the main power switch, and a clean window for the touchscreen. For the ESP32 power, I reused an old 5 volt phone charger. I opened the charger, removed the unnecessary plastic case. I modeled the case so the parts fit tightly and the cables had proper routing. I also added mounting holes for zip ties so nothing could move around inside. I added a mounting hole so the relay could be bolted to the aluminum chassis for heat transfer and grounding. The hot plate was grounded and the entire chassis was grounded as well. After soldering the mains cables, both on the phone charger input and on the main power switch, I used UV resin to secure the joints. This locked the wires in place and added extra insulation so the connections were solid and properly isolated. I'll make the code and the wiring public on GitHub. In the meantime, if you have any questions about the wiring or anything else, just drop a comment below. After I built the frame and assembled the rails, the first problem I had was the wheels. The y-axis was way too tight and the motion was not smooth. To fix it, I removed the inner wheels and used only the outer wheels on each side. After that, the rail moved much more freely and the whole stage felt smoother. Then I noticed another mechanical problem. I mounted the power box a little too low. When I installed it, it hit the x-axis, so I had to remove everything and move the power box a bit higher. After that, I ran into the temperature sensor issue. I had left a 6mm gap between the hot plate and the aluminum plate, and I placed the sensor inside that gap. And that was a disaster. The sensor reading was too high, while the surface of the aluminum plate was still too low. The heat transfer and temperature control were unreliable. First, I tried to improve the gap setup instead of redesigning everything. I took a 6mm fiberglass gasket and pushed it into the gap between the hot plate and the aluminum plate, mainly around the edge. The gap was really tight, so I used an Allen key to push the gasket into place and make sure it stayed seated where I wanted it. After that, I populated 2 PCBs and tested again. It worked a little better, but the difference between the sensor reading and the actual surface temperature of the aluminum plate was still too large. The second solution I tried was moving the temperature sensor to the center. I drilled a hole so the sensor could pass through and sit on the other side of the plate. When I drilled the hole, I secured the sensor with ceramic cement to make sure it had solid contact. And there was no air gap. But the problem was that the sensor wires were still running through the gap, and the temperature difference between the sensor and the aluminum surface was still too big. So this change did not improve much, and the readings were still not good. After that, I moved the sensor to the top of the aluminum plate, and I noticed it was a little better. Then I realized the big mistake I had been making. I had the sensor wire trapped between the hot plate and the aluminum plate. The wire acted like a heat conductor and transferred heat directly to the sensor, so the sensor temperature was much higher than the actual surface temperature of the plate. That was the main reason the readings were so wrong. Even with the sensor on top, the hot plate still struggled to bring the aluminum plate up to temperature because of the gap. At that point, I decided I had to remove the gap completely. The gap was originally meant to help the aluminum plate heat more evenly, but in reality, it was acting like an insulator, so I used my old aluminum plate as a base, stacked the two aluminum plates together, and screwed both plates directly to the hot plate. That finally fixed it. I still had some runaway and tuning to do, and I needed to modify the software so I could adjust it in the settings, but the reflow worked this time. Thanks for watching. I'll put the code and wiring on GitHub. If you have any questions, drop a comment down below and don't forget to subscribe.